Alright, so our last video for section 11.2 is going to deal with line symmetry. And when we talk about line symmetry, we need to understand what that means. And so what we say is that, in simple terms, a figure has line symmetry if you can fold it in half and one side lies on top of the other. So for example, if you were to take a piece of paper, and you can do this now, if you were to take it out of your notebook, fold it in half, and then take a set of scissors and cut from the folded side just any shape that you want, and then open it back up, that line that you folded is going to be a line of symmetry. Meaning that when you take the right side of that figure and you fold it and lie it on top of that, fold it across that line, it's going to lie on top of the left side. And so when that happens, then the figure is said to have line symmetry. Now, depending on your figure, you may have multiple lines of symmetry. And so when we talk about this line of symmetry, it's the idea of being able to fold something across that line and it lie on top of each other. Exactly. Perfect. Okay? And so you've got some examples here on the screen. In figure A, there are 3 lines of symmetry. You've got this line that goes vertically from top to bottom, where if you were to take the right side and fold it over on the left side, it would line up perfectly. It would fit perfectly on top of that figure. But it also has other lines of symmetry. So there is one that goes diagonally from left to right up. This one. And if you were to fold this figure along that line, you could see that top part would lie on top of the bottom part perfectly. And then you also have this other line going in the other direction that also is considered a line of symmetry, where if you were to take the top part, fold it along that line, it would lie on top of the bottom part. And sometimes you have a lot of lines of symmetry. Sometimes you only have one. Sometimes you don't have any. And so as we look at some figures here, you're going to kind of see that. So figure B, it does have a line of symmetry, but there's only one. It is the line that goes horizontal across the figure, and you can see it drawn there. And if you were to take that figure and fold it down on top of the top part on top of the bottom part, you would see that it lies perfectly on top of each other. You know, we use the word symmetric if you were to decorate a house. Some people like things to be very symmetric, meaning they like stuff on the left side to be the same as the stuff on the right side. Maybe not exactly the same, but they do like those two sides, both sides of the room to look very similar, be the same height, or maybe even have the same stuff on both sides. Some people like things asymmetric, meaning you maybe like something really tall on one side and really short on the other, where it looks off balance maybe. So when we talk about this line of symmetry, it's the idea of left sides equal the right side, or tops equal the same as the bottom as far as what it looks like. For that figure B, it makes me think of a paper airplane. If you were to make a paper airplane, the way you start is you fold the paper in half. You fold stuff on the right side. You fold the same stuff on the left side. And if you were to open it back up, you would see the line of symmetry right down the middle, where the left side should be equal to the right side. And so that's sort of what I think about when I look at figure B. Now, figure C, and we're talking about the star shape here. This is on a piece of quilt, but we're just looking at the star shape. It has multiple lines of symmetry. So it has one that goes vertically up and down through the middle. If you were to take that star shape and fold it on top of itself, you would obviously see that it does lie on top of itself. It's also got one here along that up to that point up here. There's also one here. You can see that. And so you can see all of those lines of symmetry, where if you were to take this thing and just fold it in along any of these lines, every time it would lie on top of each other. Okay, so it is possible to have several lines of symmetry. And then in figure D, I don't know what this is supposed to be. It looks like a boat to me. Maybe that's what it is. I don't know. But it does have a line of symmetry. Right down the middle, vertically, you can see that. If you were to take the right side and fold it on top of the left side or vice versa, you would see that you do get the same exact thing on both sides. So what I want us to do is look at each of these figures and identify how many lines of symmetry they have. Okay, so I'm going to do this in a different color here. So on figure A, the first thing I notice is that if I were to draw a line directly down the center from top to bottom, I would be able to split that figure in half where the right side could lie on top of the left side. And then I could do the same thing, go in this direction. And I could do the same thing, go in this direction. But I also could do the same thing from each of those vertices. So if I took this there, and if I took it from there to here, and then across it horizontally, you would see that each of those are lines of symmetry. So the question here is, how many lines of symmetry does this have? There's not any other lines, because if I were to take, for example, a line that went through here, well, obviously I'm not splitting that where the left side's equal to the right side or top's equal bottom or whatever, and so that's not going to work. So the only lines of symmetry are the ones that I've drawn in blue, and so there's, we start here with this one, 1, 2, 3, 4, 5, 6, and then when we get back to this one, we're starting over, right? We've already counted that line. So there are 6 lines of symmetry, and you can see each of those there in red pop up. And mine's pretty close to that. And again, you can see the answer down here as being 6. So, look at the next one. And I would encourage you to pause the video and try to do the next 3 examples here, now that you hopefully understand what a line of symmetry is. So if you want to pause the video, give you 3 seconds quickly. 1, 2, 3. All right. And so if you did pause the video and found those lines of symmetry, hopefully you're able to answer this question without a lot of issues. Figure B only has 1 line of symmetry. It is this line that goes vertically up and down the figure. Because again, if you were to fold left side to right side or vice versa, you would see they lie on top of each other. This one does not have any other lines of symmetry. There's nowhere horizontally or diagonally that we could fold it and it be on top of each other. So this one only has 1 line of symmetry. And you can see that there, mine's pretty close. For figure C, there is a line of symmetry that runs vertically up and down. There's also another one, though, that runs horizontally across right to left, because, again, if you were to fold the top down to the bottom or bottom to the top, you would see that they are lying on top of each other. Again, there's not one diagonally in any direction, and so that one only has 2 lines of symmetry. Again, you can see the ones in red that pop up. And then look at D. So it's possible this one maybe gave you a little bit of issue. There's not a line of symmetry vertically, because you can't draw a line straight down top to bottom and be able to have a place where it would fold on top of each other. There's also not one horizontally, and there's not one diagonally. So you maybe thought about going diagonally this way. And if you did, the problem with that is this part at the bottom, if you were to fold it over, would be going here. which obviously is not going to lie on top of this segment up here. Okay, so that is not going to have a line of symmetry at all, so the answer here is 0. And again, you can see that there. If there's any questions that you have about lines of symmetry, obviously let me know. Now, I want to talk about rotational symmetry, or what we're going to refer to as turn symmetry. I'm going to use the term rotational, but turn symmetry is also a common phrase. So when we talk about rotational symmetry, what we're talking about is if you were to take the figure and just twist it. And I think about like if you were going to open a doorknob, you would turn it to the right or turn it to the left. I think most people turn it to the right. If you were going to open a doorknob and turn it right, well, it's rotating, and it's rotating around the center. If you've ever taken a doorknob apart, you know there's a piece that runs from the center of that doorknob through the other side to the other side of the doorknob, and so that rotation happens around that point. What we know as the turn center. Okay, it's going to be a term that we use because we're rotating around a point. And so when we talk about rotational symmetry, what we mean is that if we can rotate a figure right or left less than 360 degrees and the figure ends up looking exactly like it started, then it is considered to have rotational symmetry. For example, in this first example here, if you were to take point A here at the top and rotate it to where point A is down here where point B is. So picture that, rotating that triangle to the right, putting point A on point B. Well, what would happen is point B then would rotate to point C, and point C would rotate back to the top. But the shape would look the exact same, and so it would have what we call rotational symmetry. And you could even do that again if you were to rotate it another 120 degrees, where point A ends up being at point C, then point C goes to point B, and point B goes to point A, and so again you have another rotational symmetry, with point O here in the middle being our turn center. The other figure also has rotational symmetry. If you were to take it and rotate it, where you take, I like to think about the top or bottom of these figures like a corner, a vertex. So if you were to take this point, we'll call it point A, and you were to rotate it down to here. Well, then what happens is this point then goes to there, and this point goes to the top. And so when that happens, you can picture that. And in fact, you could even take, if you're looking at your phone, for example, watching this video, you could take your phone and twist it. And when you twist it, you could turn it and see, oh yeah, that looks exactly like it did when I looked at it straight. And so you can kind of picture this in your head, or maybe even turn your device. If you're using an iPad or whatever, you could rotate that and see how that rotational symmetry works. So what we want to do is we want to identify the rotational symmetry, but we want to also know the amount of rotation. Okay, so this is something that you really kind of have to think about. We've talked a lot about how a lot of this is to get you to think. Geometry is kind of designed that way. So you can probably picture figure A as having rotational symmetry, knowing that if I twist this thing, if I were to turn it to the right and take this point at the top, again we'll call it point A, if I rotated it to here, then every other point would rotate, and this point would go to the top, and it would look exactly like it does currently. And then I could do that again where I rotate point A down to here. And then I could do that again to where I rotate it to there. And then I could do it again to where I rotate it here. And then if I did it one last time, I would get it back to the top. And so this does have rotational symmetry. And so we want to know, well, how much do I have to turn it to be able to get that rotation? So we know that a full rotation is 360 degrees. And if you think about how many times you would have to turn it to get it back to the top, you could turn it once, twice, 3 times, 4 times, 5 times to get it back to the top. And so if you take 360 and divide it by 5, you're going to find that it's 72 degrees. So for our first rotation, if we rotate it 72 degrees, that's going to be our first rotational symmetry. And then if you rotate it another 72 degrees, you're going to have 144 degrees to get to the second rotation. And then you can just keep adding the 72 each time. And so if you add 72 again, you're going to have, 216, I believe. And so, again, just continue to rotate that. So we're going to get 216 here. And then if we rotate it another 72 degrees, we're going to get 288. Again, keep your degree symbol there. And then if you were to rotate that last time, you're going to get the 360 to get back to the top. And so we're not going to count that 360 because we're not worried about getting back to the top. We want to know how many times can we rotate it and it still look the same. If you rotate it 360 degrees, it is the same figure. And so we're really just looking at the other 4. And so there's 72 degrees, 144, 216, and 288. And you can see those each there. Now, again, I'd encourage you to pause the video, try to do parts B and C by yourself. See how many rotations there are and figure out the amount of rotation that would have to happen to get the rotational symmetry. So if you're going to do that, I'll give you about 3 seconds to pause the video. Alright, so if you've paused that and hopefully tried this on your own, again, let's think about what's going to happen. If we, again, call this point at the top, we'll call it point 8 again. To get our first rotational symmetry, we would need to take that point to here. And when we put it there, we would have our first rotation where it looks exactly like it starts out as. And then we could rotate it again to where we put point A here. And then we could rotate it again to where we put point 8 there. And there. And there. And then the last time would put us back where we started. That's the full 360. So, the number of rotations is 1, 2, 3, 4, 5, and then again 6 to get us back up to the top, back to the 360. And so to figure out how much rotation, we're going to take the 360, we're going to divide it by the number of full rotations, which is 6. And 360 divided by 6 is going to be 60. And so what you find is that 60 degrees is going to give you that first rotational symmetry. And so if you continue to rotate it 60 degrees, we're going to have 120 degrees. And then if you rotate it again 60 degrees, we'll have 180. And then do that again and you'll have 240. And do that again and you'll have 300. And if you do that the last time, you end up with 360, that full rotation. Again, we don't want this one. We're not worried about that one because that is not a symmetry. That's just the same figure. And so our symmetry, rotational symmetry, for each one is 60 degrees, 120 degrees, 180, 240, and 300. And then on the last figure, you may have to kind of think about this one a little bit, about how could I take this and twist it and make it be the same as it currently is. So this looks like the Chevrolet logo, and if I were going to take a point and rotate it, this point is the one that I think about. Again, we'll call it point A. And so if I wanted to rotate this and it be the same figure, I would need to take that point and rotate it all the way to there. If I could put point A there, then the figure would still look the same. But then the only other rotation is to take it back and put it back here. And so the number of rotations to get all the way back around is only 2. And so you know that 360 divided by 2 is 180. And so this first rotation is 180 degrees. And that is the only rotation that we have for that one that gives us a rotational symmetry. Again, if you have questions about that, please let me know. So, if a figure can be rotated 180 degrees and have rotational symmetry, then it is considered to have what we call point symmetry, or point symmetry around that turn center. And so if you look at these last 3 that we did, the first one does not have turn symmetry, because point symmetry, because if you were to take that figure and rotate it 180 degrees, that would take point A and put it here. Well, there's not a point that it would match up with, and so that would not work. However, figures B and C both do have point symmetry, because you can rotate them 180 degrees around that point and have the same figure. So each of these, again, do have that. If you were to take this point and rotate it 180 degrees, or make a full half turn, then you would put that point here at the bottom, and it would still look the same as it started with. On the circle, you could do the same thing. We'll call that point A. If you were to rotate all that down here to the bottom, then it would also have point symmetry. And you could do that with this one. We'll call this point B. If you were to rotate it to there, in a full half turn, it would look the exact same. And then you could even do that with this Z shape. So if you take this point, we'll call it point C, and rotate it to there, then it would still have the same figure. And so that too has what we call point symmetry. And so geometric figures that are in a plane can be classified according to the number of symmetries that they have. And so we use lines of symmetry and turn symmetries to define various types of quadrilaterals normally used in geometry. So consider this. A triangle is described as having one line of symmetry and no turn symmetries. What could that triangle look like? So think about that. It's a triangle. It has one line of symmetry. It has no turn symmetries. What are the possibilities? Well, if it has a line of symmetry, and it has exactly one line of symmetry, then it would have to be an isosceles triangle. Because in an isosceles triangle, you have two sides that are congruent. And if you were to draw, this is not a very good drawing, but if you were to draw your line of symmetry, you could fold that on top of the other, and you would have a symmetric figure. If it has no turn symmetry, so think about how a triangle could have a turn symmetry. It's only going to have a turn symmetry if it's equilateral. Because if you were to take, in this example, this point at the top, and you were to rotate it to here, well, then it's not going to look the same. Because this shorter side, this one down here, is not going to be the same as the other two. So it's not going to line up. And if you were to rotate that point all the way to here, it also is not going to line up. And so because of that, it's not going to have any turn symmetry. And so really our only option is that it has to be an isosceles triangle. And you can see that here in this example. Now, if there are any questions that you have about symmetries, feel free to let me know. I expect there to be some questions, so if you do have some, please email me and let me know. This does finish section